So I've always been really fascinated by some of like the really big questions of our universe. Like, why is it so big? Why is it expanding? Is it expanding into something? Like all these big things that you hear about in like, pop science, cosmology videos and stuff.
And cosmology is because my personal interest is like understanding fundamental physics and fundamental laws of the universe.
What really actually got me super interested was this outreach event that happened at my middle school. There was someone just set up a telescope outside in the basketball court, and we all just lined up and looked at the rings around Saturn around dusk, which was just like really mind blowing to me. And I was like, "Ooh, I need to know more about everything that's going on out there."
There are a lot of challenges that, for example, brought me to the field and motivated me to start doing this as I would like it to be my job now, so as a possible job.
Yeah, I mean, originally I was interested in trying to learn about fundamental physics. Um, a long time ago, I planned to be a particle physicist, but then I learned about cosmology when I was in college, and just the rapid interplay between theory and observation that characterizes modern cosmology, I just find and still find so invigorating.
One of the new results is we have this amazing new map of the sky, and I can't stop staring at it. It's this, you know, I think it's amazing. We just stare at this image, and it's an image of the beginning of the universe, and it's just there, and we can see it. And I actually love that our image reveals so much that you can like see through everything else on the way to it. Like if you look at this new image, you see it through like the Milky Way and then out through these like little spotty galaxies that are, billions of light years away. And then further and further, and there's CMB, which is, the picture of the baby universe. It's so tangible that we get to look back in time. I think it's amazing.
And so we now have these beautiful maps that span a large part of the sky, but you can zoom in like all the way and you find all this beautiful small detail. So it's kind of cool that we didn't compromise. We just did everything. And so that was possible for the first time, I think is very cool. And from that you get all these, possibilities to look for new things in the sky.
I'm really excited about the fact that we spent all this time to make these huge area maps, which is painful because you have to wait a long time to kind of get the treasures out of the maps because you have to build up the sensitivity on them. But it was something that we aimed at, and then we actually got this ability to have huge amount of area of the sky that we have to new types of depth and resolution in intensity and polarization.
What's very new about this is that we have a new high precision measurement of the early universe, particularly coming from the E-mode polarization of the CMB, which we've now observed at high resolution for the first time. This basically gives us a new independent test of the cosmological model in a completely uncharted terrain.
In cosmology, almost every cosmological paper always says, does this agree with observation by Planck, which was the satellite that observed the CMB a decade ago? And Planck has such a great measurement of the larger scale CMB that every cosmology paper says, like, is this comparable to Planck? Does this agree with Planck? How does this compare to Planck? And this is ACT-DR6 is going to be a point where we look at the same thing as Planck, but we are independent of Planck, and we can get to the same level of accuracy as Planck. So we're having the first check of, do we agree with Planck, but also by measuring the same thing, do we agree with Planck?
And so we have one model that works really well, the lambda CDM model, but there are other ideas that are floating around throughout the scientific community. And one of the big results is that we used this new ACT data to try and see if any of those new ideas provided a better explanation for what we see in the data.
If you can think of the Taste It Now Make It challenge from Hell's Kitchen, where they're given a dish, they can see the dish, they taste it and figure out what's it made out of and how much stuff goes into it. That's kind of like cosmology in astrophysics. We can't do experiments. We get data, we see it, and we have to figure out, what types of models do we think fit this, and, what are the components of the universe that match our data, things like that.
I co-led the analysis of beyond lambda CDM cosmological models. So personally, I studied things like dark radiation scenarios, scenarios with early dark energy, scenarios with variations of fundamental constants, all sorts of interesting things, dark matter annihilation. We tested a huge swath of different types of new physics models.
And so I worked on the isocurvature analysis as well as the modified recombination analysis. And I also worked some on some of the other analyses and the interpretation of the results, particularly in the context of cosmological concordance.
I've been working on analyzing this dark matter baryon scattering model with the new ACT-DR6 data. This model is really interesting because typically we think of dark matter as cold and collisionless. And so this model adds another non-gravitational interaction between dark matter and baryons. So the dark matter and the baryons scatter off of each other and they transfer heat and momentum.
I started my PhD 4 years ago, and I was told this data release is something we're working towards. I started my PhD just after the previous one, ACT-DR4, came out, and I was initially just told, you're going to learn doing some things that might be useful for ACT-DR6. And I was thought, well, you can do these things, so maybe you can do them for ACT-DR6. And then I ended up doing basically just almost all of 4 years just working on ACT-DR6. And now that I finished my PhD half a year ago, but now I finally get to actually finish this as well, which is really cool.
So my contribution to the paper was working with colleagues to come up with constraints on the amount of the dark content of the universe that can be made of axions.
One of the things that I was working on for ACT is to try to look at things in a model-independent way for how we model our early universe.
I've been contributing to the constraints on models that involve neutrinos. Okay, so these elusive particles that we know exist, so they're part of the standard model of particle physics, but let's say we don't know enough in some sense about them. And I've been contributing to the part in the ACT paper that basically studies constraints on neutrino properties.
A large part of my work was to look at actually the planets in our solar system and looking how those planets look in our data. And because we understand the planets very well, you can sort of decipher what the telescope did to the signal. And through that, you can calibrate this effect.
Since the beginning of my PhD, I was involved in the post-spectrum development of the post-spectrum pipeline, characterization of the data, so of the maps that we got for with ACT-DR6, and assessing the consistency of this beautiful data set.
Making sure that we understand essentially what are the error bars on our measurement of the CMB power spectrum, and can we trust them? Because of course, when we make a measurement, half of the story is actually the measurement itself, and then the other half of the story is what is our confidence range on this measurement. And so both of these things have to be correct in order for us to translate the data, statements about the data, into statements about some model for the underlying physics.
Yeah, so my role in the collaboration was to act as a co-lead of the power spectrum analysis, which is kind of a technical thing, but it's basically, you have this map of the cosmic microwave background, and you want to extract the statistical property of the map because this is what you can compare to your theoretical model.
I'm primarily an instrument builder, so my main role and contribution to the whole program is designing the telescope, building the telescope, designing the receivers, building the receivers, keeping them running for a long time, way past their expiration date, and to get the data. In fact, most of the data that's in this most recent press release happens after the expiration date of the telescope. The telescope was supposed to last 10 years, and we kept it going for 15. So one aspect of the challenge is basically coming up with how to build these instruments. And so they're exceptionally complicated. You're trying to measure microkelvin sort of fluctuations on the sky in the presence of a telescope which is 300 Kelvin. So many orders of magnitude differences in the thing you're trying to measure and your environment.
So we use what's called maximum likelihood map making. And it's a type of image reconstruction on the sky that you can prove is unbiased and optimal. It's very easy mathematical proof, and I've sort of just accepted that. But it turns out when you look carefully at it, it is only unbiased if you're right about how your data behaves. It's sort of like garbage in, garbage out. If you make the wrong assumptions about what your data is doing, then you will not recover the right image of the sky. And what I learned during this analysis is that this doesn't just have the sort of obvious effects you would expect. For example, we assume that the sky is made of little pixels when we try to recover an image of the sky. But of course, the real sky is not made of pixels. It's a smooth field. But you would think that that assumption will maybe only have some effect on, the pixel scale, maybe a tiny, super small scale effect. But this is wrong. This actually turns out to have effects on the largest scales on the sky in the presence of correlated noise. And I didn't know this, and I think almost nobody in the field knew this at this time. So this is something that John Sievers discovered, and that John Sievers and I were some of the first people to work on.
So I think the thing that was hard this time is that we're trying to push into smaller and smaller uncertainties. We're measuring something with precision that hasn't been measured before, and so you go into this new regime.
A really challenging thing is the level at which we're trying to press the data to fit this model of the entire universe for the power spectrum. And it means that we care hugely about very small details and possible changes in the really detailed shape of the power spectrum. And so that means that you need to look at absolutely anything that could change any aspect of the power spectrum.